Hello, my name is Rudra and today we're going to be going over Relativity Part 1, Events. This was the second part in the series about special relativity and relativity in general. And it's seen as the sequel to the first video on relativity, which was about the introduction to relativity. So let's recap that video. In the introduction to relativity video, we laid the foundations for special relativity by introducing Galilean relativity, frames of reference, and the speed of light. Remember, the speed of light must be c in all inertial reference frames. C is approximately equal to 3 times 10 to the power of 8 meters per second. And inertial reference frames are those that are non-accelerating. However, to truly understand relativity, we need to learn more about the true nature of events and measurements. So an event is a physical activity that takes place at a definite point in time and at a definite instant space. For example, a ball hitting the ground is an event. But that doesn't just have. That's not the only event in the path of a ball. When it reaches a certain point in space, it's an event. When it's first being dropped, it's an event. When it finally settles down, hits the ground, and hits the ground, never to rise again, is an event. So these events can all be represented in the 4 dimensions by the 4 coordinates x, y, z, and t in frame S. The first 3 are spatial dimensions, and the fourth one is time, a temporal dimension, and they can be represented in frame S apostrophe by x apostrophe, y apostrophe, z apostrophe, and t apostrophe. So 2 events are simultaneous if they take place at the same time in the same reference frame. So what this means is that if I see a bird crash into a telephone pole and a ball hitting the ground, if in my frame of reference, whether I'm going at constant velocity or I'm staying the same or I'm just at rest, we see that the 2 events are simultaneous if I can measure them to take place at the same time. And this doesn't, as like I said again, this doesn't depend on which reference frame I'm going at initially. For example, a ball could be measured at either 300 in one reference frame or 5-20 in another reference frame, depending on how fast I'm going, which direction I'm going, and all these things. We can measure simultaneity. No, regardless of any of these things, we can still measure whether something's simultaneous in that reference frame. So 2 observers, and then the final point is that 2 observers do not need to perceive an event at the same time treated as simultaneous. So if person X over here, so if this tree falls down, then person X over here will obviously perceive it faster than person Y, since they're closer by and light only travels at a set speed. But then if X and Y can work out the calculations, if X and Y can work out the calculations, then they can see that it happened, and they can agree that it happened at the same time in a particular reference frame, and they can compare that with another event, then they can treat those 2 events as simultaneous. And this brings us to an important point which will help set the scale for some of the mind-bending things in relativity. It's called the relativity of simultaneity. It's not entirely difficult, but it has a lot of steps and a complicated concept to grasp at first. So let's start with this. There's person B, and when we're facing them, we see box 2 we see light 2 on their right and light 1 on their left. So we see that if the box, and they're standing on top of the light detector box. So the box turns green if the right wave, aka wave 2, reaches first, and the box turns red if the light waves reach simultaneously. A is an observer like us, they're standing here. So let's see it from A's frame of reference, or A's point of view. Oh, and also the whole contraption is moving at a set velocity in this direction. So let's first see it from our point of view, or A's point of view. So both the waves, so we know that 1 and 2 fire at the same time. So in reference frame A. So we see that these 2 are going at the same time, while person beta or person B is going at this direction. Therefore, even though they go at the same time, the box will run into the light detector box will encounter the light wave 2 first, and we can see that light wave number 2 is the first reached detector. Since the right wave reached first, then the box would turn green. So that's it from A's point of view. But then from B's point of view, we see that the box and the lights are all traveling in this direction at the same velocity. Therefore, when they fire, then they hit the person at the same time, and therefore the box would turn red. Now, this may be a startling conclusion, because the box cannot be green and red at the same time. It's not like person A can just perceive a green box, while person B will perceive a red box. That's not how it works even in a universe with relativity. So how do we resolve this conflict? Well, we made one very important assumption here, And that's why scenario B altogether is incorrect. While we know that the firing of the things is simultaneous in A, however, we should not have assumed that the firing of things were simultaneous in B. And I'll show you why in this final one. So we see that in B, for the right one to reach first, then as the whole contraption is going to the right, then 2 would have to fire first, intersect the box, and then only 1 would fire. Well, so that would make it so that it reaches this person A, simultaneously. So therefore, from person two's point of view, light detector 2 fired first. And now this isn't just a matter of perception. Where person 2 believes the light detector fired first or saw it happen first because they're closer to that one. No, it's actually because in the different frames of reference, two events in that frame of reference are actually not simultaneous. Meaning, and this is a very important point, 2 events are not simultaneous. Simultaneous in all reference frames. So this brings us to an important aspect of relativity. It doesn't just bend space, it also bends time. Or also, rather, time is perceived differently by different people. For example, so we see that even though from my reference frame 2 events are simultaneous, for a person in a rocket ship going by at half the speed of light, those events are not necessarily simultaneous. In fact, they may happen a large distance apart. It all points down to this one conclusion. 2 events occurring simultaneously in frame S are not simultaneous in any other reference frame. And this is just a preview to all other aspects of relativity and how time and space are not the same for everyone. Previously in Galilean relativity, we saw that space is not the same for everyone. But now that we introduced the concept of light and demonstrated it using this visual example above, we see that 2 events occurring simultaneously in a reference frame S are only simultaneous in that reference frame and that reference frame alone. And that sets the stage for the rest of relativity, which will be coming in upcoming videos. Thank you very much for watching this video, and please subscribe to the channel if you have not already.